Today we will be learning about transformers. Not these kinds of transformers, these kinds of transformers. So, what is a transformer? It is a device that is used in the transmission of electrical power. There are two types of transformers. What is first a step-up transformer, which increases the alternating voltage that comes from the plants before transmission in the cables, and a step-down transformer that lowers the voltage supply that reaches the customers. The number of secondary coils is larger than the number of primary coils in a step-up transformer, and the number of secondary coils is lower than the number of primary coils in a step-down transformer. A transformer works by making use of electromagnetic induction, as we had previously learned about. It consists basically of a soft iron core with a primary coil of wires wound around one side and a second coil of wires wound on the opposite side. An alternating current is passed through the coils of the primary coil. The current produces a magnetic field, but the field will alternate in direction as the current keeps alternating in direction. The iron core links the alternating magnetic field to the secondary coils. As the magnetic field lines cut across the secondary coils, an alternating EMF is induced in the coils. Next to our formula. The secondary output voltage divided by the primary output voltage is equal to the number of turns in the secondary coil divided by the number of turns in the primary coil. So we have our formula Vs over Vp equals to Ns over Np. That comes about from what we had previously learned about electromagnetic induction. Remember that if there are more turns in the coil, then there is a greater induced EMF. So it is a direct relationship. So we have our direct ratio formula here. The Vs and the Ns correspond with each other, and the Vp and the Np correspond with each other. The Ns over Np is known as the turns ratio. Next, we should know that if a transformer is 100% efficient, in theory, the output power will be equal to the input power. So, formula we've previously learned about electricity, P equals IV, power is equal to current times voltage. So, the output voltage multiplied by the output current will be equal to the input voltage multiplied by the input current. So, we have our second formula here, Vs Is is equals to Vp Ip. If we combine those two formulas, we'll see that Ip over Is is equal to Vs over Vp, which is equal to Ns over Np. The key thing to note here with this overall formula is that the number of turns of the coil and the voltage, those are directly proportional to each other. The Vs corresponds with the Ns and the Vp corresponds with the Np. But when it comes to the current, it is inversely proportional. Ip corresponds with Vs and Is corresponds with Vp. Same thing goes for the current and the number of turns of the coil. Np corresponds with Is and Ns corresponds with Ip. So let's look at an example here. Consider a step-down transformer. The primary coil consists of 5,500 turns and is connected to 110 volts AC mains. The secondary coil supplies a current of 4 amperes at 12 volts alternating current. If the transformer is considered to be 100% efficient, A. How many turns are there on the secondary coil? B. What is the current in the primary coil? C. What is the power in the secondary coil? So, identifying our variables, we'll see that the number of turns in the primary coil is 5,500. The primary voltage is 110 volts. The secondary voltage is 12 volts. And our secondary number of coils is the unknown that we're looking for. So our formula Np over Ns equals Vp over Vs. Substituting our values, we will end up multiplying 12 volts times 5,500 and divide that by 110 volts to get the number of turns in the secondary coil, and that works out to 600 turns. Remember that this problem said it was a step-down transformer. So that should tell us that automatically when we find the number of turns in the secondary coil, it should be less than the number of turns in the primary coil. Since we got 600, which is less than 5,500, that is an indication that we are on the right track. If you had worked this out and gotten a number that was more than 5,500, that would automatically let you know that you are incorrect, because if it's a step-down transformer as stated in the problem, the secondary turns cannot be more than the primary turns. Part B, we're looking for the primary current. We know the secondary current is 4 amperes. The primary voltage and the secondary voltage are the same as before. But our formula now, remember, the current and the voltage are inversely proportional to each other. So IS corresponds to VP, and then IP corresponds to VS. So when we substitute our values, we will end up multiplying 12 volts times 4 amperes and divide that by 110 volts, which will work out to 0.44 amperes. It is actually 0.436, but rounded off to 2 decimal places, 0.44 amperes. And then part C, the easiest part. The secondary power is equal to the secondary current multiplied by the secondary voltage. So the secondary current is 4 amperes and the secondary voltage is 12 volts. 4 times 12 gives you 48 watts. And if, let's say, in this problem you were asked after this to find the primary power, then it would be the same 48 watts because the assumption in this problem is that it is 100% efficient. So the input power and output power would be the same. However, in reality, transformers are never actually 100% efficient. Transformers lose energy in 4 ways. The first way, heat that is generated because of resistance in wires. So engineers, what they do is they use thick copper wires to try and minimize those heat losses. Why thick copper wires? Because as we had learned before, the thinner the wire, then the more resistance there is. The more resistance, then the more heat is generated. So the thicker the wire, less resistance, less heat will be generated. Number 2, flux leakage to the environment. What do we mean by flux leakage to the environment? When the magnetic field is just lost out into space. So to minimize that energy loss, engineers make the core into a U shape. The U shape keeps the magnetic field within the iron core, and that way it is concentrated and used towards producing an induced EMF. The third way, hysteresis, which is the process of magnetizing and demagnetizing the core. So to minimize that energy loss, engineers used a soft iron core. Why iron instead of steel? As we had previously learned before, iron has a high permeability and a low retentivity, which means that it makes for a good temporary magnet because it is easy to magnetize and just as easy to demagnetize. If steel was used instead, then it would take a lot of energy to magnetize the steel and demagnetize the steel. But since iron is used instead, you don't use a lot of energy in doing that. And the fourth one, eddy currents, that is random stray currents. Anytime if you have a thick piece of metal, the current won't flow directly from one end to the end. That's why we usually use thin pieces of wire to transmit electricity. Because then when it's thin, there is just basically one pathway for the current to go. But if it's a big block of metal, then the current can go any which way. It doesn't normally just flow from one end to the other end because there's 3 dimensions. So what they do is they take the iron core and they slice it into thinner portions and they laminate it. Once it's laminated, it's insulated so the electricity can't flow from one slice to another slice. And so it just goes where it's supposed to in a straight line. Next time, we'll be learning about the transmission of electricity.